By this point in organic chemistry, you've come across many different features of organic molecules and many reactions that you can use to turn one feature into another. So in this video, I'm going to write each of those features down and see how you can connect them. So let's think about some of those features. First, you've learned about alkanes. Those are hydrocarbons that just have all single bonds. Then you've learned about alkenes. Those are hydrocarbons that have at least one double bond. And you've learned about alkynes. Those are hydrocarbons that have at least one triple bond. Sort of in the same reactive area as the double bonds, in Organic Chemistry 1, you've learned about alkyl halides. Now this X here, capital X in organic chemistry, means any halogen. Just like a capital R means any carbon, a capital X means any halogen, so that would be like fluorine, chlorine, bromine, or iodine. That's what that capital X means. So you can have alkyl halides. You can also have alcohols. We've spent a lot of time exploring those in this chapter. And sort of in the same reactive area as alkynes, you have aldehydes and ketones. An aldehyde is where you have a carbonyl with a hydrogen on one side, and a ketone is where you have a carbonyl with carbons on both sides. So if you think of maybe organic reactions, if you think of this as a sort of map, these features here would be like mountain ranges or different areas, different regions of the map. And what we want to do is to be able to travel from one area on this map to any other. We want to know the roads in order to change any one of these features on a molecule into another. So first, let's start with alkanes. Alkanes are very unreactive. Really, there are only two things you could do with them. You could light them on fire. You would get carbon dioxide and a bunch of energy. And you might do that, for example, in your car. That's what gasoline is, a bunch of alkanes, and you light them on fire, get carbon dioxide and energy. In organic chemistry, that's not very synthetically useful. You pretty much destroy your molecule that way. So in terms of things that are synthetically useful, the one reaction of alkanes that's synthetically useful is putting in a halogen on them by using a radical reaction. So here, you would want to remember that NBS, N-bromosuccinimide, and light will add a halogen onto an alkane. Now, the focus of this video is making connections, and in general, you can gauge your education by how many connections you can make between things, how many new connections you can make between things. The difference between a novice and an expert is how many connections you can make. Experts see a lot of connections to between what they know and the world around them, and novices don't see as many. So the focus of this video is to make connections. It's not to explore the nitty-gritty details of these reactions. Now you'll need to know those, but those details are explored in previous videos, either that I have posted for this chapter or that I have posted in the review playlist for Organic Chemistry 1. So here, we're just trying to see how they connect. And I do have a video in the review playlist for Organic Chemistry 1 that explores using N-bromosuccinimide and light to do a radical reaction. So you'd see what NBS looks like, how it works, etc. For now, for this video, what we need to know is that alkanes can turn into alkyl halides by adding N-bromosuccinimide, NBS, and light. This H nu, that V-looking thing is really the Greek lowercase letter nu. H nu stands for light. Okay, so far so good. Now let's try alkenes. You can take an alkene and turn an alkene into an alkane by doing hydrogenation. So you can bubble hydrogen gas through there, and you could either add platinum, palladium, or nickel. I'm just going to add platinum here, but you could use platinum, palladium, or nickel. You could turn an alkene into an alkyl halide in a couple ways. You could do hydrohalogenation, so HX, remember that X is any halogen, that would be Markovnikov addition, or you could do that same hydrohalogenation, HX, in the presence of peroxides, and that would give you anti-Markovnikov addition. Now, I'm mentioning those mechanistic details. You'll need to know those, but I'm not going to write them in or focus on explaining those individually in this video. You could also go from an alkyl halide to an alkene. That would be through an elimination reaction. The alkyl halide could act as a leaving group, and if you add a base, that would take that off, that would rip that off of the molecule. Now, you could either add a skinny base or a bulky base to make that elimination reaction happen. For skinny bases, you would want to know something like sodium hydroxide or sodium methoxide or sodium ethoxide. Any of those would be fine. You don't have to write more than one, just one of those. And for bulky bases, you'd want to know potassium tert-butoxide. That's TBU-OK. Skinny bases will give you the Zaitsev product as your major product. So that's the Zaitsev product. And bulky bases would give you the Hoffman product as your major product. Remember that the Zaitsev product is the alkene that is more substituted, and the Hoffman product is the alkene that's less substituted. And there are videos in the Organic Chemistry 1 review playlist that go over that. Okay. Then you could turn an alkyl halide into an alcohol. Really, you could replace the halogen with an OH by doing a substitution reaction. Now, you could do an SN1 reaction. That would be if you had a tertiary alkyl halide, and the reagent you'd want to use is water. Or you could do an SN2 reaction. That's if you had a primary or secondary alkyl halide, and the reagent you'd want to use there is sodium hydroxide. Or you could also take the alcohol and turn it back into an alkyl halide. Now, with this one, again, you're replacing the OH with the halogen, so it's a substitution. So you could either have an SN1 reaction or SN2. And it also depends on what halogen you want. So say you want to, let's go through the SN1. If you wanted to do an SN1 reaction, and you'd do that if your alcohol was tertiary, if you wanted to replace it with a chlorine, then you would add HCl. If you wanted to replace it with a bromine, you'd add HBr. On the other hand, if it was an SN2 reaction, if you had a primary or secondary alcohol, then you wanted to replace it with a chlorine, then you'd add thionyl chloride and pyridine. Or if you wanted a bromine, phosphorus tribromide. And these are all reactions that we explored in this chapter and that are explored in depth with previous videos. Okay. We could also take an alcohol and get an alkene. And that would be through an elimination reaction. So we could take the alcohol and we can do an E1 reaction, or we can do an E2 reaction. For an E1 reaction, you'd use concentrated sulfuric acid, and you'd want to do the E1 reaction if you had a tertiary alcohol. And for E1, the Zaitsev product is always the major product. If you wanted to do an E2 reaction, it's going to be 2 steps. The first step is to add tosyl chloride and pyridine. That turns the OH into a good leaving group, and then it's just like your regular E2 reaction. So you could have a skinny base or a bulky base. And so, for example, you could use sodium methoxide or sodium hydroxide or sodium ethoxide as the skinny base, and that would give you the Zaitsev product, and the bulky base you'd want to know is potassium tert-butoxide, and that would give you the Hoffman product. So you can see the similarity between the other elimination reaction we had before. Okay, you could also take this alkene and get an alcohol. So it's kind of an awkward arrow there. But there are 3 ways to turn that alkene into an alcohol. There's acid-catalyzed hydration, so that was just where you mixed the alkene with H3O+. And that would give you Markovnikov addition, and you may get rearrangement. You could also have oxymercuration demercuration, so that's if you had mercuric acetate, so HgOAc2 and water in your first step. Second step, sodium borohydride. That's Markovnikov addition, but you will not get rearrangement. And in the third case, you'd have hydroboration oxidation. So that's where you'd have 9-BBN in the first step, and sodium hydroxide and hydrogen peroxide in the second step, and that would give you anti-Markovnikov addition. Okay, so much for alcohols. Now, how about going from an alkene to an alkyne? We could do that too. That's a 3-step process, and you would have learned this in Organic Chemistry 1. The first step is adding Br2. So that adds a Br to each of the carbons in the double bond. That's 2 leaving groups. Then if you add excess strong base, so sodium amide, that will eliminate both of those leaving groups and create 2 pi bonds. And then you'd shake that up with water to stabilize any charges you may have made. You could also go from the alkyne back to the alkene. And there were 2 ways you could do that. You could add hydrogen gas and Lindlar's catalyst. That would give you the cis alkene. Or you could use dissolving metal reduction, and that would give you the trans alkene. And dissolving metal reduction was solid sodium in liquid ammonia. You could also take an alkyne and go all the way to an alkane. That's if you just did regular old hydrogenation with hydrogen gas and platinum, palladium, or nickel. Okay, so these are all the reactions you have learned, and we're making these connections. Okay, we could take the alkyne and we could turn them into an aldehyde or a ketone. First, either by doing sort of acid-catalyzed hydration. So you'd take water, sulfuric acid, and mercuric sulfate, HgSO4. And if you have a terminal alkyne, what this will do is it will add the OH Markovnikov, and then you'll get ketoenol tautomerism. And so you'd end up with a ketone on a terminal alkyne. Another thing you can do is hydroboration oxidation. So you could have 9-BBN followed by first sodium hydroxide and hydrogen peroxide. And that would give you anti-Markovnikov addition of an OH, and then you'd have ketoenol tautomerism that would turn a terminal alkyne into an aldehyde. I'm using a lot of jargon here, but all this jargon is something that you would have covered in Organic Chemistry 1, and that's available to you for review in the Organic Chemistry 1 review video playlist. Okay, just one more sort of group of connections, and that's between these 2 groups here. You can turn the aldehyde or the ketone, you can turn that into an alcohol. And actually, let me just make a little room here. So you can turn those into an alcohol, aldehyde or ketone into an alcohol, by doing a reduction. Right here you have 2 bonds to an electronegative element, here you only have 1, so you can do a reduction. You can either use a weak reducing agent like sodium borohydride, or you can use a strong reducing agent like lithium aluminum hydride. And remember, this will only reduce aldehydes or ketones. This strong reducing agent will also reduce esters or carboxylic acids. And you can also go in the opposite direction. You can do oxidation. You could do oxidation with a weak oxidizing agent like PCC and methylene chloride. That would take a primary alcohol, to an aldehyde, or a secondary alcohol to a ketone. Or you could use a strong oxidizing agent, like sodium dichromate in water and sulfuric acid. That would take a primary alcohol to a carboxylic acid, actually, and a secondary alcohol to a ketone. So this is sort of really a bird's eye view of all the stuff you should know at this point. And really, if this seems overwhelming, it's only because maybe you would need to review a lot of Organic Chemistry 1. So if this will be overwhelming or not, depending on how rigorous your Organic Chemistry 1 course was. And this is a pattern that you will see throughout this semester. The effort that you put in early on to master things will pay off for the rest of your time in organic chemistry. And anything that you didn't master early on will haunt you for the rest of your time in organic chemistry. Organic chemistry is an inherently cumulative subject. The new stuff, the stuff that we really learned in this, the only thing that's new that we learned in this chapter was this, down here in purple. Everything else you would have seen in Organic Chemistry 1. So if you've mastered Organic Chemistry 1, then this chapter and this next section will be very reasonable. But if not, I've budgeted a little more time at the beginning of the semester for you to review the rest of this stuff. So hopefully by the point you're working ahead, you've mastered everything else in the chapter already, and now you can really focus on these reactions. So these next problems we're going to do, the multi-step synthesis problems, what they'll do is they will give you one molecule, and they'll give you the product, and they'll ask you, how do you turn the starting material into the product? And for these multi-step syntheses, you'll always need to use more than one of these reagents here. So, for example, what they'll do is they could give you an alkane and ask you to turn that into an aldehyde or a ketone. And notice that there are many ways you could do that. There are many paths you can take, many journeys you can go on that would take you from that starting point to that ending point. For example, you could use NBS and light to go to the alkyl halide. And then you can do a substitution reaction to go to the alcohol, and then you can do an oxidation reaction to get to your product, your aldehyde or ketone. On the other hand, you could do NBS and light to get to the alkyl halide. Then you can do an elimination reaction to get to the alkene. And you can turn the alkene into an alkyne, and then you can do hydration with either acid catalyzed hydration or hydrogenation oxidation to get the aldehyde or ketone. And both of those paths will create that transformation. So there are many, many correct ways. There are many correct answers for that transformation. There are many ways to get from point A to point B. These problems are going to be very non-linear. They're going to be like solving puzzles, fitting different pieces together rather than just walking in a straight line. The last thing I want to point out before we start to do these problems is there are stages and there are steps to studying for them. There are two big stages. The first stage is knowing each of these reactions by heart. Now that means knowing the reagents themselves and knowing the mechanistic details. So things like Zaitsev product or Hoffman product. Things like rearrangement or no rearrangement. Things like Markovnikov addition or anti-Markovnikov addition. So knowing those mechanistic details and all of these recipes, that's the first step. And really you kind of have to do that before you even start to practice the problems. So that if you're studying for synthesis exercises, the first step is just know the reactions cold, master them. Once you've mastered them, you're able to start to think through them. Once you've memorized them, that's when you want to start to try these next exercises in the chapter. And when you get stuck, refer to the video. Now, because there are many ways to solve these, for example, the yellow way or the gray way in this picture, what I show you in the video may be different from what you have, and what you have may be correct. So if you think that that might happen, please visit me during my office hours. I would love to see your different creative solutions. What I present in the videos is just one possibility, one way to think through the problem. And that is how you want to use the videos. You don't want to use the videos as something to just memorize. You memorize how to turn one thing to another. Because the molecules you have on the test, although the concepts behind solving them will be the same, the molecules themselves will be different. Right? The homework questions won't be the exact same as the test questions. So the important thing is to learn how to think through and analyze the synthesis questions. And that's what I'm trying to give you an example of in these next videos. For now, I wanted to give you this bird's eye view of how to change these different functional groups. Aldehydes, ketones, alcohols, alkenes, alkynes, alkyl halides, how to change functional groups. This whole table is a table about how to change functional groups. Oops. So we're going to use this table in future exercises to help create transformations in molecules.